All right, on to section 6.3. This is going to be a real quick summary of electron configuration and a couple terms that are key with electron configuration when we talk about how we do electron configuration. And the first one of those key slides or key terms is going to be the Pauli exclusion principle. And we've been talking about quantum numbers, and all the Pauli exclusion principle says is that no two electrons can have the same exact set of all four quantum numbers. They can have 3 out of 4, but never can they have all 4. And remember, in regards to last year, and we talked about this, have you ever seen two houses on the same block with the same address? No. They're pretty close, all right? They're very similar, but no two houses on the same block have the same address, and that's the same way with quantum numbers. No electron can have the same exact 4 identical quantum numbers. So they're all separate. So let's talk about electron configuration a little bit. We have a couple things here. Remember, electron configuration is when we do the 1s2, 2s2, 2p6, 3s2, 3p6, on and on and on and on. Now, just for your reference, I want to review what that looks like. All right, if you take a snapshot of this picture right here, this is kind of the order in which the energy levels go. So if you follow the arrows down, you're first going to do 1s. Then, if you follow the second arrow down from the back to the front, 2s. Then we go 2p, 3s. Then we go 3p, 4s. 3d, 4p, 5s. 4d, 5p, 6s. And this should be reviewed from last year. Remember that all the s orbitals, or angular momentum numbers, can hold 2 electrons. P's can hold 6, D's can hold 10, and F's can hold 14. Regardless of what their energy level is, all the S's hold 2, P's 6, D's 10, and F's 14. So when we go back and we look at electron configuration, the 4, remember you have 3 pieces of information here. The 4 represents the energy level, or the principal quantum number. The P is going to represent the orbital or the sublevel, which is really essentially the angular momentum number. And then the 5 is just going to represent the number of electrons in that orbital. So we have done a couple of examples with electron configuration, but let's just go ahead and let's review how we would do one. I'm going to pick a very simple element like fluorine. So I'm going to choose an element like fluorine. Now, fluorine has 9 electrons. So what you would do is you're going to follow the energy levels until you hit 9 electrons. So using that last slide that I showed you, 1s can hold 2, 2s can hold 2. So we're at 4 total electrons. Our next energy level is 2p. 2p can hold up to 6, but do we need 6? No, we only need 5, and we add up our total number of electrons. 2 plus 2 plus 5 gives us 9. So the configuration for fluorine is 1s2, 2s2, 2p5. Now, if we're going to do the orbital notation, remember, S only has 1 orbital, so we're going to go line for the orbital with 1s. 2s only has 1 orbital. We're going to do a line for 2s. And 2p has 3 orbitals, so we're going to go 1, 2, 3, 2p. Now, S is filled with electrons, so I'm going to go up and down. And remember, the reason we go up and down is because the up represents an electron spinning clockwise. The down represents an electron spinning counterclockwise. We'll do the same for 2s2, up, down. Then for 2p, we have 5. We're going to go up, up, up. Remember, each orbital has to have 1 electron before you go back and put in a second. So we went up, up, up. We're going to come back and go down, down. And that is the orbital notation for fluorine. Now, we're going to talk about a couple other things here real quick. You may remember doing the abbreviated method. And the abbreviated method involves going back to the last noble gas. Well, from fluorine, you go back to the last noble gas, and you put it in brackets. So the last noble gas is helium. And then you're going to start going forward from helium. Well, after helium is lithium, which is going to start at 2s2, 2p5, which would be the remainder of your abbreviated. So the abbreviated configuration for fluorine is helium in brackets, 2s2, 2p5. Just want to review that because you might see that. So remember, you always abbreviate from the noble gas because the noble gas has all the noble gases have a complete outer shell. So there's electron configuration. A couple things with electron configuration. Here's an orbital diagram that we just got done showing. Instead of using lines, I use boxes. You can do either or, whatever your personal preference is. We have boxes for the orbitals or lines for the orbitals, and then arrows representing the number of electrons. Now, as I mentioned, the direction of the arrow, up or down, is in direct correlation with the spin of the electron. One thing with the orbitals, and I got done talking about this, but the specific name of this rule is Hund's rule. And Hund's rule is saying that each orbital in an energy level must have at least one electron in it before you go back and put a second electron in. So if we look at the example for nitrogen here, we went up, down, and then here for 2p, we go up, up, up. Right. That is Hund's rule. Hund's rule states again that you have to have at least one electron in each orbital before you put the second one in. So that is Hund's rule. Now, if we look at the periodic table here real quickly, we fill in increasing energy level order. So we've talked about this. If you look at the energy level, the alkali and alkaline earth metals are all in the S block, 1s through 7s. The transition metals are in the D block. Everything to the right of the transition metals, so the metalloids and the nonmetals, are in the P block. And then the actinides and lanthanides are in the F block. So if you follow the arrows in order, that'll take you all the way down through the periodic table in order. There are a couple anomalies with the periodic table. So if you're looking here, all of a sudden you're looking, and now where do we get anomalies? Well, that happens right here. For instance, right, the actual electron configuration for copper is 4s1 3d5 instead of the expected 4s2 3d4. Now, why does that happen? Well, it happens for a couple of reasons. And the first reason is this. The 4s and 3d energy level are very, very close to one another. So the S and D energy levels are very close to one another. Now, if we obey Hund's rule states that each orbital wants to have one electron in its outer shell. So if we go 4s and 3d, right, you would expect the configuration to look like this. Up, down for 4s, and then up, 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 up. So if you take a look at it, that's what you would expect. However, since 4s and 3d are so close, you can almost say that there are 6 orbitals to fill instead of this 4s separately and 3d separately. So since they are so close, we're going to follow Hund's rule. What we're going to do is we're going to have an up, 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 up. And this actually satisfies the energy of the electrons better than having the 4s completely filled, since 4s and 3d are so close to one another. Each one of them has one electron in its outer shell, which is more pleasing to them than having the 4s filled and the 3d having one orbital empty. So there are small anomalies throughout the periodic table, but there's just kind of one example of how that would work. So if you say right here, the last anomaly, 4s and 3d are very close. This also occurs when you're going from s to the f orbitals as well, with a couple of those atoms. So there are a handful of anomalies on the periodic table, and you just want to, we're not going to go through them all, but a classic question on the AP test would be explain why the configuration of copper is 4s1 3d5 instead of 4s2 3d4. And the example or the explanation is that their energy levels are so close they almost behave together. So that is kind of the end of Chapter 6. We'll have a very, very brief quiz on Chapter 6 very shortly here. So be prepared to talk about and review everything that we've done in Chapter 6.